Whenever you're going to be constructing something and that thing got two different materials, it is eventually a composite. You know, even the reinforced concrete beams that you've all have designed before. So a reinforced concrete beam, let me choose a different color. So let's say you all have designed, or you know what we are. We got this cross section, which is just a rectangular beam, and it's got some reinforcement, right? This is actually a composite section. This is basically a composite because it's got the gray concrete and it's got the steel. And the way we bond the steel with concrete is by some ribs around the steel bars. It's going to make the two sections work together. It will make the two sections resist stresses together and get strained together. So that's basically, it's a composite by its own, right? So even this reinforced concrete sections, it is actually composite. Exactly like what the student just said to us, when we have two different materials, and we manage to interlock those two materials together, then it is basically a composite. And that's it. We're going to see these kind of systems applied in the construction at various levels, right? So let's have a look. This image here, it's again taken from a textbook, which can talk about different composite systems here. Like this one shows me, yeah, maybe two, I would say for now. First, you got composite between the concrete slab. So this slab here, see, this is the concrete slab. It is actually in composite with the bars. And also the whole reinforced concrete section, it is in composite with the bonding. This is a metal sheet. You see this kind of coming up with this special profile shape. This is a metal sheet. We use it a lot in the construction. It's got two main functions. Number one, it's going to help to improve the strength and, you know, add that composite feature and make it strong. And number two, it's going to help to work as a formwork, as a permanent formwork to carry the wet concrete. So you don't need to spend a lot of timber to form up the slab. The bond is going to be there. You just need sometimes to put one propping line to carry it. So the first system I can see here, it is the slabs. The slab is in composite with the bonding or the metal sheet. Okay, so they're gonna the metal sheet's gonna act as reinforcement to resist whatever tension it needs to take. Remember, the tension for most of the slabs are in the bottom because they are simply supported, or they got the positive bending as well. Now, someone gonna ask me, what about when you get over the support, you're gonna have negative? Well, that's where we're gonna put additional top reinforcement. Okay. So this is one of them. Here, one of them is we got the slab is in composite with the bonding. Number two, can someone tell me where is the there is a second composite action we can see in this image? What was it?
Steel framing.
Excellent. The steel beam, whether this guy, the small steel beam, or this guy, the big steel beam, it is in composite with what? With the slab itself. Okay, so if I give you a cross section there, like if I cut through here, and I will try to draw what's going on there. There is an I section. This is an I section for the steel beam. Right. Then on top of the steel beam, we will be welding what we call a shear studs. We have to weld them. You're going to be full strength, but weld to the top. So these guys, they are the shear studs. They are welded it's up to the engineer. 250, 300, 200 millimeters, they welded. And they're going to interlock the gray concrete. Let me make it in a different color. The gray concrete will be, I'm making it here orange. Oh, that's fine. So this is the concrete and it will actually be working together. So why we interlocking them? Because we want to make sure they're going to be stressed together and strained together. Okay, they are interlocked together. So you know, I'm not sure if you did engineering, if you remember, there is a stress strain diagram. I don't want to take it too much for engineering, but if you understand, or when you design the steel, or we had what we call it stress strain curve, if you remember. Now, the point is, when we have a strain, there is no difference. Wherever we're straining the concrete, we're going to be straining the steel. So that's the point. We need to make sure practically we have managed to interlock the two materials, so they're going to be strained together. They're going to be kind of deformed together. That's maybe the easier word. And if you manage to do this physically, then your section is composite. So when we manage to have our section composite, then if this is under positive bending, what we did here, basically, we made all the slab to take compression. When we have positive bending, all the slab will take the compression, which is good. We know the concrete is very, very good with compression. And that's what we want here. Because we know, if you remember, in the portal frame, one of the weaknesses with the portal frames, when we had a portal frame with an I section, one of the weaknesses we had is the top flange will get buckled when it's under compression, and that's why we need to put that's why we need to lock it in with purlins, or use fly brace and all these kind of techniques. But here, no, we're going to actually stabilize the top flange because it won't get buckled due to compression, and again, the strength going to be way improved. So that's again a composite section. So in summary, this slide really talks to you about two major types. We're going to be visiting, I think, in this today. Yeah, we're going to be talking slowly about the first type, which is the slab in composite with the bonding, right? So the slab in composite with the bonding is the first system. And then I will show you examples for situations where the entire slab is in composite with the beam, with the steel beam. Okay, that's the second type. I'm seeing actually in this image, there's obviously no composite action between a column and a slab. This is just not the case here, or it's not. Basically, we do have something, but we're going to see at the very end of the lecture notes. We have composite columns, where especially for hollow sections. This is a hollow section column. I'm just drawing the plan section view for a column. It's like you have a hollow section column, like a square hollow section, SHS, and then we fill the inside with concrete, and that will give us very well improved capacity. So again, we've got a hollow section. We still can do composite with these sections, but you need to do a formula. So we will talk about composite columns at the end of the notes. So I think we're going to see how many types we got there. The first one, it is the slab in composite with bonding. The second one, the entire slab, it is in composite with the steel beams. Here we go. This one can show you a clear image for the two systems I mentioned. First, you can see here from the bottom bonding. And if you go walk in many car parks in the CBD or shopping centers, you will see, look from below, especially if we are like for apartments, because we're going to have different plaster boards that will, just let me clarify something. Is one of the issues with bonding, talking about this bonding, it does not resist fire. And if you want to resist fire between apartments, you have to put special plasterboard materials. Now, in car parks, this is not achievable. You won't be putting a plaster under the concrete slab. So that's why sometimes you're going to see in car parks, if fire rating is required, you're going to need to not use bonding. You may not see bonding below because you want concrete to resist it. Sometimes I can tell you some builders still tell you design the slab to be fire rating and just still use bonding for me because I want it to help me in forming the slab and carrying the slab. So I can tell you in many projects, even if you see in car parks, bonding, if you see it from below, sometimes there may be additional reinforcement. That's what we're going to see in the design as well. There may be additional reinforcement in the slab that will help with fire resistance, right? So there are situations where still people gonna think about using the bonding slab because they're gonna be adding more reinforcement in the bottom, more than required, to help with fire. In case fire happen, the bonding obviously gonna lose integrity, gonna lose its capacity. So the slab will be relying on the bars, on the steel bars at the bottom to carry what it have to carry. So again, we will know more and more about this. I will let you use some tables, some span tables to make those decisions. So that was one type of composite. One is between the slab and the metal deck, which is this one. And number two, it is the steel beams. I can see the steel beams here. The steel beams, these steel beams, they are, I know it's not clear. We can't see the shear studs, but it's very obvious that they have used a bonding, a composite system between the entire slabs and the steel beam. So there should be some shear studs welded on top of the steel beams, and they will make everything in composite to each other. Here in this picture, if you zoom in a bit, you can see we have a bond beam. This is something maybe touching what you are doing with your assignment. Yeah, you do have assignment working on. We all know about it. How are you going with the assignments? Perfect. Answer, that means yes. All good. So you all know with your assignments, we talked about having band beams, and between the band beams, we're going to have bonding. And I talked to you about use of bonding from the start of the semester. We used it in many in the school project as well. I've defined it to you, but again, this week we're talking about its more details about its construction, right? Yeah, what we're trying to show you with this slide is the bonded slabs can also be used in a banded beam slabs, not only with steel. So here, definitely, we don't have composite steel beams. With the slabs, we have normal band beams, we all know. And then over the band beams, we're going to put the bonding sheets to have composite slabs. Any questions? Right now, this slide talks to us about most of what I've covered to you. So, for example, it is an economic consideration to use composite in composite systems because they're going to be giving us more strength with reduced steel. So there's economic considerations. What the composite system is about. It's about just that profiled steel decking. To let you know, again, there are different brand names in the market. There is Condic, there is Bondic. There are more and more available. Some of them got more profiling details, which makes the bond more robust and more firm. Now, if you need to use the Bondics for longer spans or for heavier duties, you would need to use strongerly profiled sheets, right? So yes, we're gonna have a look to these kind of types, but why we would need to go stronger in case your slab is carrying more load and you need more kind of heavy duty bonding. So as I've already briefed you, the steel decking acts as a permanent formwork. So it's going to stay there forever. And the good thing, you don't need to spend a lot of money in renting formworks and carry your wet concrete. However, still you need to prop the bonding. If your span you're pouring, let me take you back to this image. If the slab here, if the span from here to there you're trying to pour was only about 2 to 3 meters, then maybe you've got a situation where you don't need to put a propping line. You don't need to prop it in the middle here. But if the span gets to be really too long and you're carrying very thick concrete, then the way it's gonna flex the bonding. We have to put a piece of timber, like a propping line, and some vertical elements to prop it. So but again, this is way safer than using a lot of propping or formwork below it. So still the bonding will help you to reduce a lot of props if you go with the conventional reinforced concrete slabs. Right, so as I've already discussed, the design concept is there is a shear bond. There's gonna be a shear bond between the bonding sheets. From the top, there is always grooves on top of the sheets that will ensure there is actually a bond between the gray concrete and the metal deck. And as I've discussed with you, we need to make sure the two materials act together compositely to reduce the requirements of additional boron reinforcement. Yeah, so as we always talked about, composite steel decking gives a double economy. Yeah, you're going to be saving in the formwork. You're going to be saving in the steel, right? Especially if you don't need to worry about fire rating. If you need to worry about fire rating, we're going to need to put a little bit more steel in the bottom. Yeah, I think this point here just repeats what we kind of talked about before. It's economy, eliminate most of the lower reinforcement. I will let you look at tables and sense that as well. There are kind of span tables where construction engineers can go through and make decisions of whether it's feasible to use composite in a project or no. Okay. Now, yeah, this is talking about when we can also have composite action between the entire slab with a steel beam. That's also a composite system we can use in the construction industry. Okay, and that's basically just repeating what I showed you with the pictures, right? Composite action in two ways can be within the slab and can be between the slab, the beams, the steel beams, and the slabs. Any question? Right, this picture shows you different brand names for the metal deck, right? So this one here, it's widely used because this is lightweight and you can see them in many. By the way, KF is just a brand name, but there's also different brand names. Now, all those types are all under one company who supplies different sheets, but still there are other companies. Maybe there's 4 to 5 famous companies used in the country. But this is coming all from one supplier and they have different profiling. As you go with more grooves, you can see here we have more grooves. More detailing in the profile, which will increase the composite bond. And when do we need that? If the span starts to get longer, if the loads starts to get higher, if the slab eventually is thicker. So we need more composite, more bond. So I can say this is number 1. It is the weakest. This gets to number 2, and this one gets to number 3 in terms of the strength. You would need maybe for a bridge, traffic loads, you would think about using this heavily profiled deck. But this is for lighter and this is even lighter. So this is here I'm talking about within the slab. But between me and you, even what you studied 5 years ago, reinforced concrete section, normal, no bonding, this is also considered composite in theory. Because whenever we have two different materials, it is the composite. What about steel beam? Steel beam by its own, would you call it composite or no? Steel beam by its own, like what you did in the portal frame. Would you call it composite?
Yes.
Yes.
Yes, because it has a lot of elements. And the connection point.
The steel beam was by its own.
The steel beam with the connection of the columns and the purlins.
They're not working. No. Okay, I got your point. You're saying because it is because we got the rafter and
Yes.
the column. But they are still steel.
All right.
This is not composite. No. Composite when you have one member, one element, right, built from two different materials, and that was not the case here.
Then, like the column and the pad footing.
But still, the column is our element, and the pad is our element by its own.
All
we
right.
did not. I know where you're coming from, but no, you won't call this. You just call it a portal frame because we have managed to connect it with all those full fixity connections. When you connect things together with full fixity connection, it does not mean you are making them in composite.
Okay.
We're talking about the framing element here, like the slab. The slab, we are making it built from a metal deck and physically connected with gray concrete. That's a composite.
Okay.
Okay. So we won't be calling none of the portal frame elements we discussed in week 2, 3 as composite. Nothing there was composite. Right? So this one we're talking about, it is here a slab, and it's in composite with the deck, with the metal deck here. That's between beam and slabs. This is the slab, and that's the steel beam. So the steel beam here will be acting together with the slab to resist whatever bending it's taking. In the portal frame, we did not have there were purlins on top. If you remember, we got purlins, and the purlins will not resist flexure with the beam. It was the purlins, yes, were helping with the fly brace or helping the top flange to restrain it and prevent its twisting, but does not mean it is composite. Composite means when they're going to be pouring gray concrete here, this whole section from the top of the slab all the way to the bottom flange can act as one member together. Okay. So that was the second system we're going to be covering this week. It is when we have composite between a steel beam, the red element here. And remember here, we did not pour the slab. Don't get confused. You know, guys, like later on, they're going to pour the concrete slab here. This image, it does not show you the concrete is poured yet. This image is only showing you, this is again from a supplier. It just showing you when it's ready to take the concrete on. This is just a heavy duty metal deck already sitting on a steel beam, and maybe next day they're gonna pour the concrete on top. And then when they pour the concrete on top, both the elements can act as one piece. Any question? Correct. That's a good point here. There should be different materials, not different parts, and they need to be bond together. The different materials have to be bond together, mechanically bond together, and resist whatever shear stresses, bending stresses, axial stresses. They have to be resisting it. So if you want me to give you some clarity here, I will just give you a cross section. Like we're gonna look from the side. So your steel beam will be, this is the steel beam. And I'll draw it in red. And the metal deck is again just a place on top, and that seems to be for me heavy duty metal deck. And to make sure they are bound together, they use the shear studs, because they want a composite between the slab and the steel beam. And also there is composite. So later on, they're going to come and pour the concrete. They're going to pour the concrete here. Yeah. And in this case, the steel beam gonna act with the slab to resist whatever load it's actually resisting, because mechanically we have managed to do this, right? And the designer will be taking into remember here there is no gap, there is no gap at this point. There is no gap because that's where the deck is sitting. But here they're gonna be a gap, and that will be considered by the designer. But I can tell you, usually in the industry, as I said in the previous, we have situations where you don't need to use bonding. It's not always a case where you use bonding. We have a composite actions without the bonding. So it's just up to you if you want to use a bonding. Sometimes we don't use the bonding, which gonna take away the voids on top of the steel beam. It was basically up to the designer, because I can tell you nowadays builders like to use bonding. It's going to save them all the formwork on top of it. All right, so now we have the different profiles. So what are these? They are the sheets that are available in the market, and we can use them to develop composite slabs. So let's quickly talk about their main features. So the sheets will come in this width about 590 or 600 wide. They're going to be as long as required into the page, and they will be placed so in pieces. If I go back to this real image, for example, if I zoom in there, so they're going to be putting this in pieces. So they go about 590 first piece. Then they're going to come and put the following piece next to it. Then they're going to come put another piece next to it, right? When they place them, they're going to interlock them together. They got this. I'm going to show you. I'm going to go back to the profile here. So when they're going to, this is the first piece they're going to place. And then they're going to come and put, you see this end? It will be interlocked here. So they're going to come, bring the other one around and place it. So that's how they do it. They can just fold it around and place the next one next to it, and that's how it's really working, right? That's what they mean interlocked together. They interlocking the 600 about 600 wide panel next to each other. So the embossment, which is these kind of little things. Yeah, these are, sometimes we have them very significant, sometimes light. It's again, as I said, up to the capacity we want to resist. So they're going to ensure that there is bond between the concrete and the steel deck. Okay. They are available in different thicknesses. Whenever you go thicker, it's more expensive. Whenever you go thicker, it means you don't need as much line of props as required. And I'm going to let you see the tables. So what I'm saying here, and like I say to you, usually builders like to go straight away, use 1 millimeter thick. Thick is the thickness of the element. How thick is the element here? So 1 millimeter means it can take longer spans without a prop, without putting a prop under. If you're going to go a little bit cheaper, 0.6, that's fine. Maybe it's possible for string, but you may need to use 1 or 2 lines of props to carry whatever it's got have to carry. The problem is with during the wet concrete. We have to carry the wet concrete when still the strength is not there. And as soon as the concrete get hard, you can take the props away. So we're going to have a look to span tables and see how to choose things. That metal deck is made from high steel strength because it's a structural member. Yeah, and hot dip galvanized usually because it's exposed, so they have to galvanize it. right? And the tensile strength, it's very close to the tensile strength of steel bars. And as I can say, theoretically, there are two ways to design those bonding to work with the slab. One of them, some engineers can find the area of the rib, the area of this nib, the steel area within this, and just they're going to say, I'm going to replace the steel bars I want there. But this is very simplified way of calculating it. Engineers don't rely on this only. There is a composite action we have to use, different theories, which we don't need to go through the design process in this subject. But one of the simplified method to design those bonding is they say this rib here can act as a steel bar. And by calculating an effective area within this zone, then they're going to say, I can tell you, ideally, the bonding can replace N16s at 300. N16s at 300 bars, it's about 1,000 millimeter square steel in 1 meter. So if you go to the steel bar tables, N16s, 16 bar diameter, every 300 millimeters, it is equivalent to about 1,000 millimeters square per meter steel area. And usually this bonding, this lightweight bonding, cover it. Just the basic rule of thumb. But again, there are careful design processes for the structure engineers to go through. But this is again, there are SPAD tables, which the construction engineers typically use to make a decision whether we go there or go that way. And still the engineers will confirm and refine things. But to make a decision about, because many projects you may receive it, not really, they don't go through the different types, because engineers can't go through all the different available types. It's up to sometimes the engineer will just design it as a classic concrete slab, or maybe it was designed as timber. Then while you are heading the project, the client, you start suggesting things, so you can make that decision to maybe they wanted to upgrade, where they wanted to change the function of the room, they wanted a better performance in terms of serviceability. And instead of going to the engineer and asking him to redesign, you can make that decision and think about all the costing that will come your end, because all that will add more costing, more work for you, and you can make decisions. But at the end of the day, the structure engineer will redocument it on their documents and the drawings. So this image is taken from the book that I will share with you. There's, as I said, a span table book which helps construction engineers to decide what bonding sheet they should use to construct particular span, carrying particular load, and for particular functions. I will share that with you today or during the workshop. So again, this image just gives you all the details you can think about. You can see the bottom side of this is a cross section in the slab. You can see this is one piece of the bonding, and here they interlocked it with another piece of bonding, right? So this is the sheet width. This is the cover width, and all these things here are the top reinforcement that we have in the slab. Sometimes, as I said, for fire rating, we will have as well bottom reinforcement we will talk about, because if we need to have the slab to do fire rating, the bonding can give you some minutes for fire rating, maybe 60 minutes, maybe less, 30 minutes fire rating. But in many projects, we need the fire rating to go for 2 hours or 1 hour and a half. If it's not enough for the bonding to do that, we're gonna put some bottom reinforcement. Okay. Right. So what else I would need to share with you? The thickness of the bonding, it is just this thickness, which I've already said to you, it can be 0.6, 0.7, 0.9, or 1 millimeters. And whenever you go higher, it's more expensive. But if you go higher, it's going to give you better strength. We're going to think the reason why we need it to be thicker, because all about supporting the wet concrete when we just poured it. We don't want it to bow. We don't want the bonding to bow and deflect significantly while we're pouring the concrete, because it's going to have a permanent deformation from day one, and we don't need to do that. Okay, so any question about those details I'm sharing with you? Is there something not making sense? This is just part of a cross section for a bonding slab or a composite slab when it's interconnected with a metal sheet. And this is just one of the brand names available in the market. And yeah, as we said, we have 2 sheets shown, and this is one of them, and this is the other one. Yeah, you can see actually the image here is talking about bottom reinforcement, and the reinforcement here is you can have it running into the page, and you can have it running parallel over the ribs as well. Yeah, we're going to look at those documents later on carefully. Now, just to let you know, if you go to your week 10, click on reading materials, you click here. Yeah, here we go. That brochure, that lies at full brochure. This is the one which that we downloaded. Let me just open it quickly. We're gonna have some time to let you practice something. It's quiet. It's got about 60 pages, and it's got. I will take you through it because these are sometimes the examples we like asking the students. I will ask you to decide on what span. We will look at this. I just don't want to. It's better to practice this during the workshop, right? It just helps you to have a quiet basic decision or preliminary decision about the material you need to use in constructing composite slabs and making a decision, because those tables will tell you the level of steel you need inside it, the thickness, the thickness of the material, as we said, and some important construction decisions you can make there. So let's leave this document. We will practice it during the workshop and some examples I'm going to bring. And this is, again, these tables are available in that document I showed you. So these tables will tell you the quantity of steel we have for the 1 millimeter bonding, or 0.6 millimeter. I was saying to you the 1000. Here we go. See the 1000 sheet. But this is, remember, this is overall. It includes the ribs and the non-ribs areas. But if you go to 1 millimeter, if you take away the bottom, which is here. So when I say 1000 millimeter per meter, we're talking about the area, the cross-section area of this. Right? And as I said to you, there are simple ways to design bonding as a steel bars. Usually we take an effective area from the ribs. So we ignore this part. We just take this part here. But these are just very conservative designs. We have different methods to do the calculations. There's another table in that book I'm going to share with you, which is just talking to us about the weights. Weights is kind of important for construction engineers to see how they can transport and place and get them ready. You cannot have a very heavy patch of bonding placed in one room on a particular slab. You have to spread it. So usually the weights is important to figure out, and those tables will tell you such information. And as I said to you, the strength, this is for the designers. The strengths can be up to 550 MPa. So these are the other types, basically. These are the other types, and they will give you much better performance, more strength, more steel. They're gonna span, they're gonna manage to carry the wet concrete at much more bigger spans, especially when you're pouring a deck for a bridge. bridge over a canal or a small kind of river. It is too complicated construction-wise to have props below it. So we need, usually we like to have less props to support the bonding. So definitely they would use something like this because it's going to help you with carrying the wet concrete and also helps you with the strength. It will give you a lot of heavy strength. So yeah, there are special features and details about this type, but this would be the really the most heavy duty option you've got around available. This one you can see it's lighter. The widely used one for residential application is something which looks like this, right? It should be enough. They are basically specified by the engineers or also can be selected by construction engineers based on this document I'm showing you here, right? They kind of almost same. They just have different geometrical arrangement. So instead of the width can be smaller because it's easier to construct. The width here is still 600. Yeah. So they're just talking about the main feature. Again, to let you, we won't ask you to memorize this kind of information in an exam. Basically, we want you to know what we mean with composite slab as a general definition, what we mean with composite slab with beam in general definition. I won't ask you to list such information, or I won't ask you to list this type of product. What we will ask you to do is to select or decide on how we can specify a composite slab for particular spanning arrangement. And that's what we're going to practice during the workshop with an example. For example, I will tell you, it's like what you have in your assignment 2 project. You will have a banded slab, and there is between the banded slab, there is maybe 3-meter span, and I will tell you, tell me what bonded metal sheets you can use. So you just need to know how to use this table, and we will practice this. So you will have your span. The spans are written here. If we said 3 meters, then it looks like we can really get it to work within something like where can I see a 3 meter? So remember, we're going to talk about what's the difference between this table and that table. I just don't want to go out of what we're talking about in our lecture. So there is visual appearance importance or not important, because this one gonna be flatter. This one will sag more. Right, we will talk about this. So if in case in your project you are interested in flat floors, like visual appearance is important, then you have to make sure the deflection is not excessive. I'm not talking about the permanent deflection from loads, what the engineers looks after. No, we're talking about the deflection that will happen by the time you pour the wet concrete on the deck. If you pour wet concrete on the deck, there's going to be a lot of heavy weight on the deck and it's going to get profile. If you don't want to have significant deformation, then you need to use these tables, right, to find out the best thickness option for you and to find out if you need props or not. So this 0 means no prop. The bonding can span all the way like 2.2 from one end to another, no bonding, or 3 meters. That's if your thickness, whenever the slab thickness is going to go higher, obviously you will end up having reduced the span. So it's really very easy to use. You just need to know about it. And my point was, that's how we're going to ask you, right? We won't ask you to list some basic terminologies related to the bonding. Okay, you just need to understand their construction process and deciding on selecting them. Right, there are, as you can see, special features, and some of them, like the supplier for this sheet, KF57, they're claiming that it has high resistance for fire. which is so be it. And again, that's going to be a choice from the architect. Maybe he wants, because maybe they didn't want to put plasterboard that can resist fire, so they may decide on having special type of bonding or formwork or metal deck. That's where they're going to go and search for such products, right? Okay, so we're talking here about the formwork, and as I said to you, we've gone through all those kind of features, but I'm going to cover them for you again. The bonding length can be, they can come as long as your transportation allows. It says here can come up to 20 if you want to get that expensive transportation arrangement. But on average, usually 12-meter transportation length will be more economical. However, depends on the spans and depends on how much you want to cut on site, because you won't have a span which is this much, obviously. But in case you want to bring them on site and cut them, you should be able to cut the bonding on site as well. But you don't want to get the exact cuts because there can be some discrepancies. You can't rely on the drawings to tell you how long the bonding is going to be. You want to bring them on site, measure the actual lengths, and then cut to the required spans, right? So they can be as long as this figure. The width, they can be, as I showed you with the detail, 590 millimeters, or can be a little bit smaller, a little bit wider. It depends on the type of profile we're using. But these numbers we see here, they are typical for the lightweight, for the usual one we use in residential constructions. As I said, deflection limits here, it's nothing to do with the permanent deflections you may have designed during your undergraduate course or what you practiced before. This is talking about the deflection when you're going to be pouring the slab on top of the bonding. So there is an option of limiting the deflection to span over 240. So if your span was about 2,400 millimeter span, that means you're going to be limiting the deflection to 10 millimeters only. So if the span in millimeters divided over this figure will give you the deflection in millimeters. So this ratio, you can see it's more than this one. That means we are worried about the look, which is for good general alignment. There is even more kind of flatter results, dividing it whenever you increase this value, right? Whenever you increase the value, it's gonna actually make it flatter, and that means for such arrangement we are worried about the finish. So, for example, you may be installing tiles on top of the concrete floors, so maybe a very large tiles. So you want to make sure your slab is quite flat, and then you'll be deciding on 270. So if I go back to the, in the first example here, I said if your span was 2240 divided on 240, sorry, no, I would say 2400. Yeah, divided on 240, that will give you 10 mil. That's for the first option. 270, it will give you less. So 2,400 divided by 270. This is only 8-9 millimeter. Let's give you about here. If we go longer spans, it's going to be more useful. In case you're not really interested, you are maybe constructing a warehouse, which is, or a storage area, you're not really interested in the visual quality, let it bit bow, it doesn't matter, and that will save a lot of money in terms of concrete. So we can go 130. Remember, these are not the deflection that will happen due to putting the loads or due to creep or due to shrinkage. They will happen because the bonding itself gonna flex as you place the wet concrete on top of it, and then as it get harder, that flex gonna stay permanently. with such profile. So here, if you're not worried about the visual appearance of the flexure, you can go as low as 130. That means the deflection that you would expect they're going to be higher. So we're talking about the same figure, 2,400 divided by 130. It's going to be about 18 millimeters. 18 millimeters. That's from day one. We're gonna bow like this even from day one, without even putting any loads. So yeah, these are what we mean with the formwork. How we're gonna think about deciding on the formwork. Main thing we need to worry about the appearance, or in other words, the deflection that can happen by the time you pour the concrete on the deck. Now, in terms of design, there are two stages. So as I said to you, stage one is prior to placing the concrete. Yeah, as I said, those metal decks, as you can imagine, they are a bit. I think there are some images that will show you people going to be walking and working on top of those metal decks. So, and you know, all these kind of activities going to be on top of it. So when the engineer design, or it's actually done in this, the engineers who have developed these tables, they have done this exercise. Then first of all, they have designed the bonded over two stages. Stage one, when it's going to be carrying the construction loads. They want to make sure they won't fail or break, and they want to make sure they won't sag a lot. The second stage, that's the first stage here. It's due to placing of concrete on top. The second one is during the placement of concrete. So that was the second stage. So stage number one, it's the construction load, which is about 150 kilograms per meter square. Number two, it is as we put the blanket, the uniform pressure from the wet concrete, which can be 200 thick, it's quite heavy. We all know how to calculate the weight of concrete. Just multiply the thickness of so 25 is the density of concrete, multiply it by 0.2, which is 0.2 meters, which is the thickness of the slab. And that will give you 5 kPa. 5 kPa is about 500 kilograms per meter square. It's quite heavy. So that's what they designed for the second stage. They're going to make sure this, if you have 200 thick slab, as a pressure on the bonding, because remember, when it's wet, nothing is carrying the gray concrete, only the bonding, right? So in summary, when those metal sheets are designed, they are designed over two separate stages. The first stage, it is when it's carrying live load. The special thing with live load or construction loads is they can come up as a point load, because people walking, people placing the materials at one spot. So it's a bit needs to be careful considerations. The second stage is when you have a pressure of concrete sitting on the bonding. Now, all those designs, they're not basically, in real practice, they're not done by the structural engineers who do the drawings. They are done by the suppliers, by the engineers who work for the supplier, like the engineers who work for bonding. They have created this document. They have gone through all those loading scenarios and all the arrangements, which is like done by LISO. Okay. So back to our notes. Yeah, these are basically the notes that we have on the formwork. Yeah, more details about the formwork, and then we can have a break. I just want to before I start looking at those tables, which is the example I was talking about, let me finish this slide. I think here we're talking about using span tables, which I was telling you, one of the main tasks we like students to practice on, it is deciding on which bonding or metal sheet to use in constructing particular slab. Right, so that's basically what we're going to go through in the coming slides. And before we talk about it, let's have maybe an 8-minute break. We'll take you through that. All right, we'll talk about selecting the metal sheets for particular project. So let's take a break up to 9, and so let's progress with our composite slab. So here we will be talking about using span tables, which you have access to from this document I'm sharing with you, and just some basic information. Bonding is used as a framework, so if you have a question, definitely, as I said, in the real practice, there are different brand names, but in a test, we will give you a set of tables from maybe Bonding, from another product, it doesn't matter for you, right? So you will be given tables in case you ask some questions like this. Temporary props are equally spaced within each slab span. Now you're going to see the tables here, the tables, regardless what type of thickness or what thickness of bonding we're talking about, they will tell you you don't need any props, 0, you need 1 prop, or you need 2 props. When we say 2 props, they're going to be equally spaced. So if this was a span, this was your span, and when we say equally spaced, that means this span is same as this span is same as this span. So they are all equally spaced. Yeah, that's what we're saying in the second point. Okay. Now let's go see the next point they putting up here. We got 2 sets of tables. One of them is when the spans that we have, they are equal. What we're talking here about in your project, you may have a project where the spans are equal or where the spans are not equal. What do I mean there? So let me just show you. For example, here, let's talk about this. It's actually clear here. So what you're seeing here, you've got a bonding. This is just taken from the textbook. You've got a bonding running over the permanent span. So this is a steel beam in your project, or a band beam, and this is a steel beam in your project, or the edge of the band beam. Remember, in your project assignment 2, your band beam was about 1.5 meter wide or 2 meters wide. You can nominate it, as we discussed. The bonding will start from the side of the band beam. You with me there? Let me, while we're talking about this particular point, let me open your project example and explain to you what I'm talking about. So here we go. Have a look to, in this example, we do have a bonding slabs as far as I remember. Here we go. So this is the school example. If I zoom in here, you have a band beam, you have a band beam here, and you have a band beam there. And between the band beams, we have a bonding slab. Why I know it's bonding is from this sign, because if you read this, it's a 300 thick slab and it's on bonding sheet. So you go simply just run your eyes down here. Yeah, it is denotes direction of bonding slab, and this is as thick as this, and it's telling us what we're doing. So what I'm trying to say to you, or when I say the spans are equal or not, we're talking about these spans. So if this span and that span, they kind of equal to each other, then we should be able to use particular table. And if they are unequal spans, then when we have to use a different table. All right, that's what we're talking about. I'm not sure if the tables are available for us here. Say that was for anyway single span. So this whole tables, they are for single spans. So we're not talking here about continuous spans. So it's just one span. Here we're talking about 2 spans, right? And pay attention to this magenta color here, equal slab spans. So what does this mean? This span, this one is equal to that one, right? 2 spans and they are equal. Now we have situations, I think we do have situations where the spans are not equal. There is, but they can vary up to 20%. So if one span was 1 meter, the other one have to be 1.2. If one span was 2 meter, the other one have to be maximum 2.4. Someone will ask me, what about if the ratio is different? It's higher. It's 1.5. Then it have to be designed by engineer. You cannot use the table because the steel reinforcement gonna change and the deformation is gonna change. Okay, so that's basically what we're talking about. And remember here, the bonding have to go continuously over. If you stopped and started the bonding, it's not a problem. So one thing I will highlight to you guys is for your project, because you're using a bonding, which it's gonna be something like this. The bonding here is never continuous. So you can consider this as single span and this as single span and this as single span. Because we do have a section that will help you to, no, actually it's not provided here, but it's in a different project I've given you. It's in the PT examples. I've given you in a PT example. No, actually it's here as well. So have a look here. Have a look here. Yeah, this is, I will zoom in. Guys, if you don't understand, ask me here. Yeah, just unmute and or send me a text. So what's this? Can someone tell me what's this? What's this I'm circling around? What's this element? Is this a plan view or elevation or a section?
It's basically it's a beam, and it's like you are watching it like cutting. You have.
So correct. Yeah, that's a section for a band B. Yes.
Yep.
So we all understand this. I do find limited number of students who still having difficulties to actually read the drawings, and that's very upsetting. This is just a cross section for a typical cross section, which is cutting the band beam and a slab. Now, this kind of, that's what I'm asking you to do in assignment 2, but adjust it as required, because at this end you have a pile cap, and at the other end you have what, a pile cap. So let me come to my point again. This is a band beam, and where is the bonding here? Where is the bonding, which is this week's topic? It's actually this thing here, steel decking. It's here, this one. You see it? It's here. We're looking to its elevation here. Now, someone will ask me, where are the ribs? Why we can't see the ribs? Can someone answer this? Why we cannot see the ribs like this? Can someone tell us why? Why we cannot see the ribs?
Is it from the other side?
Well done. Yeah, that's it. Yeah. Yeah, I mean, maybe these questions are simple, but I do see very odd answers. And we need to know these things. So that's right, because the ribs are running this way. The ribs are running this way. You don't see them. You're seeing them from the side. So anyway, my other point is the bonding here, is it simply supported or continuous? You give me this answer. The bonding, is it simply supported or continuous over 2 spans?
It is simply supported.
That's right. It is simply supported. So you don't need to worry. If I go back to these tables, you don't need to worry about whether it's equally spanned or unequal span with these different. So this is like in your project, it's basically simply supported because you have the bond beams. You have the band beams. Usually in construction, like this one as well. If I pay attention here, you see there's a gap. So it was decided to actually have it as simply supported. If we had another steel beam here in the middle, right, then this bonding will be continuous over 2 spans. That's where you're going to have 2 spans. If your metal sheet stops and starts, then it's not continuous. All right. So basically that was this point here. There are 2 sets in the tables. One of them is talking about the long span over the short span is actually 1, or we got situations where the spans are not equal. The long span over the short span is more than 1, but still less than 0.2. And what we're here talking about, we're talking about cases where our bonding is running over 2 spans. Okay, and you have to make sure you're choosing the right table. Depends on the question you received and the project you're working with. So pay attention to this when you, if the question came to you in a test. But for your project, we all agreed that because we're using band beams, we're typically going to have single span. So this kind of arrangement does not impact us. Point number 4 here is talking about the density of concrete. We all know that from before. It is 24 kPa or 2,400 kilograms per meter cube. You need to understand the bearing. So usually the bearing at any end, it is 50 millimeter. We're talking about here. That's this end here. We have to be 50 millimeter. That's when it's sitting on a slab. Now for band beams, we can make it less because the concrete is actually we're having it sitting on the band beam, right? Now another point here, it is 100 millimeter intermediate. And you need, if as I said, if you got your bonding continued over a steel beam, you need to make sure that the width of the top flange should be more than 100 millimeter. So they say in intermediate flanges, you need to have, like if you have your slab running over, this is the intermediate bearing, this have to be minimum 100 millimeters. Right, and at the ends, if it's sitting on a steel beam, it needs to be 50 millimeters. But with bonding, because we have steel, we're gonna make it 40. Maximum construction loads, that's again, this is all comes from the document, from the engineers who did this document. The engineers who did this document, they're all giving us, sorry, talking about this document, we're gonna practice during the workshop. They have gave us these specifications. They're all written here for you, and we've just summarized them to you on the slides. So you know what kind of information you have to be looking at. So this kind of telling you the maximum construction loads the engineers has considered when they made the span tables. The workmen and equipment 100 kilograms, which is about 1 kPa. Mounting of concrete 300 kilograms. So that's 3 kPa. We're talking here mounting of concrete, not stacking of not placement for the concrete slab, right? Because placement of the concrete slab can be higher than this. It's going to be up to 500 and depends on your design. Stacking of materials can be minimized. So you just need to make sure you distribute the materials as much as you can to be within these kind of figures. No splicing or jointing of sheets. That you can, there are no arrangements where you want to say, I'm going to be welding things here or doing any arrangement. This is unachievable unless designed for specific purposes, but reasons by the engineers. You cannot splice it and then claim it's going to be continuous. You cannot do these kind of things, right? And there is no cantilever portions. Yeah, it's always have to be supported at 2 points. If it's cantilever, then don't think you're going to get advantage from composite action. You can place it there to help you as a formwork, but it won't be the case. So using the table is really easy. You just need to carefully read the question and see which table is applicable. If you have a project like your assignment 2, where you got band beams, and you know it's simply supported or single span, then you just need to find out if your slab thickness was 200, for example, then you can decide what was the span between the band beams. You just, for example, if I go to this project, we just need to, whether you nominated it or you're going to work this from the architectural drawings. Usually architectural drawings will give us all the dimensions, so we just need to measure this span from this point to that point. Let's say this was 3 meters from this point to that point. Then I need to decide what bonding to use. So I jump back to my table here. And can someone kind of, by looking to this, make a decision with me? If the span, we got singly supported span. So let's say this is our kind of project again. I will open it for you and I will put a dimension here for you. The span from this point to that point was, say, 3,100. Why I'm saying 100? I'm just allowing for the 40 mil here and the 40 mil there. You remember when we looked to this section? Yes, this is our bonding. I'm zooming to it, sorry. This is our bonding, and we're saying we're gonna have 40 mil this side and 40 mil the other side here. Now, someone will ask, didn't we say 50? Now, for bonding, I think the documents or the suppliers will accept it for band beams. When you want to support the bonding on the edge of a band beams, we will be able to go only 40 millimeters because we need to allow for the ligatures. We're going to have ligatures here, unlike steel beam. And this was acceptable because the friction coefficient between the bonding and the concrete is higher than the friction of coefficient between the steel and steel. You can imagine if you put steel on steel, it's going to be more slippery than steel on concrete. So it is accepted to have only 40 millimeter bearing for bonding to be on top of concrete band beam, right? So going back to what I was talking about, I said to you, assume the span here is 3,000 or 3 meters, right? And I just said 3,100, allowing for those ends, which is 3,080 mil, but let's make it 3,100. So if we have 3,100, can you tell me what option I can use here if my slab thickness was 200 millimeter? Not need that much. Any answer? I'll come back to that comment, but let me talk about this. Your slab is 200 thick. The span is 3,100. Which bonding type you will be able to use and how many props you need from it? Any answer? Yes, perfect. Yeah, that's it. Yeah, easy. We unfortunately we didn't have the chance to have no props. Yeah. We didn't get the chance to use no props. And we simply just gonna be going with this option. So this is what we can use. And yeah, that's basically, let me go to this comment here. What was this about? No cross-section view, not cross-section. I don't know what this meant to be. If you were talking about this, no, it was actually cross-section. This was cross-section view. Not sure what you mean, no cross-section. This is a cross-section view for a slab sitting on a band beam. Jomi, is it clear to you?
Yes, sir. I just talking about longitudinal cross section. That's it.
Okay, I know what you mean. Yeah, that's right. So I think when I was asking why we cannot see the ribs, he said to me because we're not cutting through the ribs. That's right. Yeah. Right. Let's go back to our notes. So I think we're all okay. But one thing I did not tell you in the question, which you guys answered, it's the question will tell you whether we have visual appearance as important. That means I'm going to keep it as flat as 1 over span over 240. The visual appearance, the question was leaving it clearly clearly indicating to you the visual appearance was not important, then you can actually use table. Now, I think you've experienced how simple is this. If anyone within the students with me have any questions here, please let me know, because I can see students in the final exam still don't answer these kind of questions, which I don't know why. I basically don't know why. And maybe they're just not attending. They just, yeah. If you have any question, if you want me to go through another example, please tell me. And we will touch on this again. I will brief you about what I did again during the workshop. Now, this table is again for what? For situations where we have continuous bonding over a support, right? Can I ask you what's the bearing we needed over the support? Did you forget it? What was the bearing required over this support here? How much bearing we need to make sure is happening there? What was the bearing we needed here? 100 millimeters. Yeah, so we have to remember these kind of main features. So the bearing here should be 100 millimeters, and as a practicing engineer, you need to make sure the top flange should be minimum, which is usually the case. It's only the steel beam going to be as small as very small channel, 200 PFC channel. It's got 75 mil top flange, which I don't think what someone going to use. If in case someone may tell me, what about if I had a project I want to use bonding and I've got just 200 PFC. The 200 PFC got 75 mil top flange. Then what you have to do, just weld another plate on top. Just weld another plate on top, and that's it. Or use a bigger PFC. Where actually the biggest PFC, yeah, 380 PFC will have 100 mil, but 300, 250 got 90. So you may end up welding a plate on top. And we said here it's going to be 50 mil. So again, these tables are talking about situations where you got the bonding continued over 2 spans. And in this case, you can simply go use this table. The new feature here you have with those tables is talking about whether the 2 spans are equal or not. If they are equal, so you're more than welcome to use these tables like what you did before. If they are not equal, you have to make sure the difference is within 20%. Right? If one span was 2 meters, the other should be 2.4, 2% different, 20% difference. If it was more, just say you have to leave it to the engineers. You have to contact the bonding company and ask them what they can do. They have their own calculations to do that for you. Okay, in a test, if you have the situation, just say it is beyond the acceptable range. You don't need to give me any answer, right? But if the spans were within what you have, then you have to give me the right answer. And I think this slide basically is taking through an example, right? These slides are taking you through an example which I did for you. Any questions about what we just practiced here? This is just another example. Let's have a look to it. Beam center line to beam center line was 6 meters. Single slab span. Use of 0.6 bottom material bonding with 120 thick slab depth. Visual appearance is important. Try no props. Allowable formwork span. It's insufficient. So they're just basically taking you slowly through the process of applying or using the tables I'm talking about. This is the single span we want to build. If we need a prop, we have to put something like this. If we need 2 props, we have to put 2 props like this. As I said, they have to be equally spaced under the span. Yeah. So they taking you here through the scenario of they tried no props. It did not work because it's only giving them 1,800. They tried 1 prop. It gave them 4,650, but not happy, was not working. Then they put 2 props. You know, all that's cost. You're going to be renting those props. Whenever you add more, it's more. Someone will say, no, as I said, told you, some builders will just say, put them all 1 millimeter. I don't care, but I don't know if 1 millimeter will give you the, let's have a look here. 1 millimeter, no, I think it will not work anyway. It will work with 1 prop. Have a look here, see, 1 millimeter bonded. 1 millimeter bond, 1 millimeter bonded. Yeah, with 1 prop will get you to 6 meters. Okay, so really it's the decision that can be made by the builder and what type of saving they want to make. Some people may have good connections with scaffolding companies, or maybe your company will got their own propping material, so it does not cost them to have it. So really it depends. Right, we talked about all these kind of things. If you got the tables, they can go up to 3 spans. So it depends on the supplier. Yeah, so in page 11, it's got that's in the book we're gonna give you, or you have access to in the reading materials. Page 12, you got equal formwork spans or different spans. Same thing with the 3 spans here. There are cases where you got equal spans or 20% difference in the spans, and we discussed about when to use when. There are just here comparisons between two different profiles. So you can, as I mentioned too, this is heavy duty. It can be for longer spans. These ones can be, but you know, other ones can give you greater bond. So it really depends on what type of loading. In the end of the day, for us, what will matter is how much strength it can carry. These ones, this kind of bonding can be used with concrete frames like your project, which is band beams. Why basically this is happening? Remember the 40 millimeter that I was talking about? This, if you're going to be using the heavy duty ones, we don't have much connection between the concrete and the bonding, because you can see in the profile here, you've got large voids. These are voids, and it won't be good exercise to have this type of deck sitting on the edge of the band beam, because only these lines will be in contact with the band beam. So, and you're losing a big gap here. However, when we have these kind of bonding, we have a very long length bearing on the edge of the band beam, and only that tiny void was there. So this is a very good option to use on concrete frames, but this one will be better used, or mostly used in a steel structures. This one still can be used on steel, won't be an issue. This one, if you are able to prop things, yeah, which is usually in residential, we are able to have one line of prop to a line of prop. So this is where it can be used. But as I said, for bridges or heavy duty constructions, usually you got very tall floors. If you've got sometimes, like in some of the towers they built, usually the first floor goes up to 9 meters in height. It's too expensive to prop for 9 meters. So your concrete slab is actually 9 meters higher than the ground. It's too expensive to prop it. So in this case, we're going to be using this heavy duty because it can span for longer spans, unpropped constructions. If you are stuck in situations where you can't really prop, you are building over a bridge, over a river, sorry, or over another canal, or the ground is far away from you, then think about using these type of decks. Yeah, formwork spans. So basically here it's going to be spanning between a steel beam to steel beam, but here it's going to rely on the bond with the concrete. So just general comparison between the heavy duty deck and the lightweight deck. That was the table talking. This slide is kind of talking about some of the details I briefed you already about. The profiling and all those dents and grooves are there to ensure there is a composite action, which I talked to you about. We need to make sure to resist the slip. I think this is another way of explaining it. What do we mean with composite action? We need to make sure when those two materials are working together, they won't be slipping from each other. We need to interlock them together. So we need to resist the slip, and that means we have to mechanically interlock the two materials together. And that's what we're doing with the profiling and all the grooving we have there. So the shape of the ribs, the thickness, and all that will help into this. And that's what the engineers take into consideration. So as a construction practicing engineer, as I said, you won't be really calculating these things from theory. You will just need to use the span tables, which I shared with you. But you need to understand, you can't decide in changing, can't make a decision in changing the profiles from one to another, because that will change the capacity and you're going to be changing the theory. You have to go back to the engineers. There are decisions made on different sites where the builder may choose a different profile, but they didn't know there was a reason to use that particular type because it was used in the calculators. So you just need to know changing the profile of the product. It's not just same. It's not only just different brand name. It can be different in the capacity we need to resist. Right, so all what we talked about so far is the bonding, sitting on carrying the concrete slab and having whatever capacity. The other details you have to, so what I'm trying to say, the tables that I shared with you does not only talk about the type of bonding we need to use in terms of the thickness, it's also, there are tables that will also help you to decide on the quantity of steel we have to use in our slab as a permanent placement of steel. So you can see this is the steel, as I said, we got situations where we're gonna need to have bottom steel to help us with either strength or fire rating. So this line here is just the steel which runs perpendicular to the ribs, and these dots, they are the steel bars running parallel to the ribs. Top reinforcement, very important. As we say, if we have negative bending over the supports, like over these locations, nobody will resist. We're gonna, as you know, the bending moment diagram, if I just draw it quickly. So the bending moment diagram for this, we all know it's like that. That's the bending moment diagram. It's all positive bending. And if we have two spans, it's going to be like that, then goes negative, then goes positive, then goes like this. Same thing here. We go positive, goes negative, go positive, negative, positive, then almost zero. So the bonding, yes, it will help us to resist the positive bending. Usually in civil engineering, the positive is at the bottom. You remember? Yeah, the bending, or that means the bending which is under the slab as diagram, it is, we call it positive because it's going to be tensioning the bottom and compressing the top. Right now, the negative bending here, it needs steel at the top to resist, so that's why we're going to have top reinforcement as well. But here in this regions, the bonding will be taking the job of resisting the tension. Okay, the bonding will be taking the job of resisting the tension. Or simply supported, it's all positive, so the bonding is doing all the job anyway. But the issue with continuous cases like 3 spans or 2 spans, we have to have top reinforcement. We have to have top reinforcement, which you can see them here. We have them running into the page, and we have the other direction. Now the other one, someone can ask me, if it's one-way slab, why do we have this bar? Why this? Because the slab is running into the page. It's like your project. You're gonna have your bonding. You know how you placed your PT, your bottom PT, your post tensioning. That's how the slab is running from one capping beam to another capping beam over the banding. So someone will tell me, why you're putting steel in the other direction? The steel there is for shrinkage. We need to have steel for shrinkage control. Okay. Sometimes we have two-way slabs if you really need to, but that's a different story. All right, so I think I've explained most of what you're seeing here. We always need to respect the cover. We have to have always cover, so there is always cover between the main bars and the top of the slab, etc., etc. So what I want to get to is there are tables which will help us to determine the quantity of steel required, whether top or bottom, for our selected slab. So step number 1, with those tables, we decided which bonding type to use and build the composite slab. Table number, the second step, we're going to use tables. Right here, we're just showing you basic diagrams, but there are going to be more tables we started doing here, and I'm going to start doing this with you during the workshop. Right, there are very easy to use tables, but just pay attention to this during the workshop. There are easy to use tables that will kind of help you determine the determine on the quantity of steel required. Like basically you just need to know what type of loading, dead load, life load, and then if you know the span, you will be able to determine the quantity of steel. This is, they're gonna tell you the steel in area, millimeter per a millimeter square in a meter. Okay, I will take you through this during the workshop. So I think we will cover this, and most of our slides this week is talking about bonding. So then I'm going to talk about some basic details, and then at the end I'm going to introduce you to other situations, but we won't have a lot of detailed situations where we got, as I said to you, you got composite columns. I will brief you about it in a few pictures, and that will be our note. So what I want you to understand, most of what we're going to be covering for our composite systems is bonding, because it's widely used in the industry. The composite slabs, that's what we're widely talking about this week, and also practicing during the workshop. So far what I did with you is I talked about up to here. I've already showed you how to select the metal deck during the workshop. I'm planning to hopefully spend 1 hour on this to take you through the exercise of nominating and specifying the top reinforcement based on using the table. Remember, the engineers, the structure engineers, they're going to be documenting all that on their drawings. But as a construction engineer, you need to, as I said, you got 70% of the projects, the engineers will make the concrete slabs as conventional concrete slabs. So you need to make a decision. Should I change it to composite or no? Should I change it to PT or no? We talked about PT already last week. So now composite. And to make this decision, you need to find out the costing for the bonding. And I think by now you know how to choose based on those tables. During the workshop, I will take you through the process of determining the quantity of steel required. Again, those images, these tables are just taken from the book that I shared with you. And like, for example, they're explaining to you what the tables are reading. It's very easy to use. Make sure you're going to attend the workshop, because these kind of the questions we like asking during the final exam. So you're going to see in the table, yeah, you have two or three figures. So see here, you've got two figures. What are those figures? They are explained to you in these slides. And basically what I did, I've just copied this from the Lyset book. That's what I did. So during the workshop, I will take you through the process of nominating and determining the quantity of steel required for composite slabs. So you can have the big picture, the full picture about the feasibility of going with a bonding slab or a composite slab rather than conventional slab. And then, as I said, after we go through this exercise, there are some definitions to go through for the slabs. Then I start talking to you about composites, columns, and that will be the end for your 10th topic, which is composite slabs. So far, just make sure decide working on assessment 2. Make sure you go through the notes we covered, let's say up to this. If you have any questions, prepare them to me. I strongly suggest you now to study for your final exam.